Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker. We're on chapter 12, part 3, multiple linear regression, the overall F-test, and the partial F-test. So if we want to conduct the partial F-test, first, we're going to state the null and alternative hypothesis. Remember, the partial F-test asks, are these additional predictors predictive of our response, given that the initial predictors, beta 1 through beta g, are already in the model? So what we're really asking is HO, beta g plus 1 up to beta k, do those all equal 0? Or are at least one of the additional predictors not equal to 0? Are at least one of the additional slopes related to those predictors not equal to 0. We are going to calculate the test statistic, which is going to require us to look at the additional sum of squares due to regression of those xg plus 1 up to xk predictors, given x1 to xg are already in the model. And the way we're going to do this is we're going to actually calculate the sum of squares due to regression of our full model and our sum of squares due to regression of the reduced model, and then look at the sum of squares error of the full model to be able to calculate this. So if HO is true, we know the distribution of our test statistic is degrees of freedom. It's an F distribution with degrees of freedom 1 equaling k minus g and degrees of freedom 2 equaling n minus k plus 1. So if we draw a picture of the distribution, right, it's an F distribution, so it looks like it's skewed right. And essentially we can set up our rejection region, reject HO, and then we have our failed to reject region, failed to reject HO. And essentially the peak is going to be around 1, right? Because that would mean that our regression is no different than random error. And we're going to set up 0.05 of the alpha area, and we can calculate the critical value under degrees of freedom 1 equaling k minus g and degrees of freedom 2 equaling n minus the quantity of k plus 1. Okay, to calculate the p-value, you can do this in R, right? We can use the probability under an F distribution that our test statistic from the partial F-test, right? Our test statistic is equal to that. We use our degrees of freedom 1, which equals k minus g, degrees of freedom 2, which equals n minus the quantity of k plus 1. And then we're going to say lower dot tail equals false because we want the area in the upper tail. So if our test statistic is beyond our critical value, so it's somewhere over here, F test statistic, then this area is going to be very small, right? Our p-value would be less than alpha in this case, and we're going to reject HO. But if our p-value is very large, that means that our test statistic fell somewhere over here, right? That would have a very large p-value, and in that case, our p-value is going to be greater than alpha. Okay, we'll go through the code in a moment, but essentially we're going to say, we're going to either look at that p-value and say, since the p-value is less than alpha, we reject HO, or we're going to say, since the p-value is greater than alpha, we fail to reject HO. If we want to interpret this in context of the problem, we're going to say those, if we reject HO, at least one of those predictors, right, have a slope that's different than 0, which means that the xg plus 1 up to xk are predictive of y when x1 to xg are already in the model, right? Dropping xg plus 1 up to xk will result in a significant decrease in the predictive value of the model. If we fail to reject HO, we're really saying that all those slopes are equal to 0, or they're not different than 0 per se. So we're saying that xg plus 1 up to xk are not predictive of y when x1 to xg are already in the model. So dropping the xg plus 1 to xk will not result in a significant decrease in the predictive value of the model. All right, so if we want to do this in R, we can start off by setting up our alpha level. So we're going to say alpha equals 0.05. Okay, we set the number of people. In this case, our N was 67 and our K was 3. Now we're going to ask ourselves, if we fit a model with just one of the predictors, are the other two predictors additionally predictive given there's already one in the model? So we're going to be working on the salary example again. And so we have K equals 3. That was the number of employees, profit margin, and the IP cost being predictive of the starting salary. And the full model has all 3 variables in the model. And we can get the sum of squares regression of the full model. We can get the mean squares of regression of the full model. And we have the sum of squares total. So from there, we can also get the sum of squares error of the full model. Okay, walking through this, we can get all the values for each of the ANOVA tables. And what we're going to do in a future video, we're going to fill these all in. But you can see that this is the actual code here if you want to carry out the partial F test, right? So these are the equations given: the sum of squares of regression of the full model minus the sum of squares regression of the reduced model divided by K minus G divided by the sum of squares error of the full model divided by N minus K plus 1. So we get a test statistic value of 17.81. Our critical value in this case was 3.14. So at the end of the day, we're going to say, yes, even if we consider a model with just one of those variables, those 2 additional variables are predictive of starting salary, even with a variable, even in addition to a model that just had one of the variables in the model. So we're going to walk through this in a future video, but I just wanted to give you a short introduction on kind of how you set up the partial F test and how you look at it. All right, I'll see you next time.